Hi, thanks for the introduction, Vivian, and thanks to the organisers for letting me talk here. So, good morning, good afternoon, everyone, wherever you are. My name is Deanna Hooper. I'm a postdoctoral researcher over at the ULB in Belgium, where it is currently 7:30 in the morning, so apologies if I seem slightly sleepy. I'm going to tell you today about a recent project I worked on together with collaborators in Brussels, where we considered the scenario of primordial black holes evaporating and producing all of the dark matter that we see in our universe today. So this far into the conference, I don't need to motivate to you why we want to look beyond the standard WIMP paradigm. Despite a huge amount of experimental effort, the WIMP particles are still extremely elusive, and we have not yet been able to detect them. Now, we've already seen this week that there are many alternatives we can consider to WIMP, such as primordial black holes constituting the dark matter or axion-like particles. Now, here I want to take a slightly different approach and consider the scenario where we still have particle dark matter, but because we no longer consider weak interaction, so I'm moving away from the WIMP paradigm, this means I can also no longer rely on freeze out to produce the correct relic abundance of dark matter we see today. So this of course calls for a new production mechanism of dark matter. So here we consider the possibility that we have a population of primordial black holes in the early universe, which are going to evaporate via Hawking radiation. Now this evaporation will source all of the standard model particles and the dark matter. And the interesting thing about this dark matter is that it can only have gravitational interactions. It doesn't need to have any other interactions. Now, one important difference between the scenario I'm considering here and the scenario we've seen this week in terms of primordial black holes is that I'm going to assume that my family of primordial black holes have completely evaporated before the time of BBN. Now, the reason to make this assumption is that we have very, very good measurements on what's happening around the time of BBN on any process injecting energy, which means if my primordial black holes are still evaporating at the time of BBN, we would spoil existing bounds. So in order to guarantee that the primordial black holes have completely evaporated before the time of Big Bang nucleosynthesis, it means we're going to focus on a very, very small mass range. So we're considering primordial black holes in the mass range of 10 to the minus 3 to 10 to the 9 grams. So if you remember the exclusion plot we've been seeing this week, this is several orders of magnitude off of the plot because it's really, really low mass primordial black holes. The nice thing about this is it does avoid observational constraints we have on primordial black holes. Now, despite the fact that this dark matter might only interact gravitationally, we can actually still constrain it, because if the dark matter is lighter than the initial primordial black hole mass, it will actually behave as non-cold dark matter, which means it can affect the growth of structures. So we can actually use different cosmological observables to constrain this scenario, even if we only have gravitational interactions. So in order to parameterize this non-cold dark matter coming from primordial black holes, all of the main information is going to be encoded in the phase-space distribution. So I'm considering a fermionic dark matter species here. So normally we would have a Fermi-Dirac distribution. However, because of the different production mechanism, my phase-space distribution is actually going to be very different. Now, the phase-space distribution is going to depend on three main parameters. First of all, we have the black hole mass at the time of formation. And I should mention here that we consider always a monochromatic mass distribution. Then we're going to have beta, which is going to be the initial abundance of the primordial black hole. So it will tell us how much of the early energy budget was dominated by primordial black holes, or was in the form of primordial black holes. Finally, I'm going to have the dark matter mass, which is going to help us fix the correct relic abundance that we see today. And I should mention here that one interesting thing that we did in the paper that was different to previous studies in this direction is we did not assume instantaneous evaporation of the primordial black holes. If you assume instantaneous evaporation, all of your dark matter is produced at the same time. If you assume non-instantaneous evaporation, obviously the phase-space distribution is slightly more complicated, but you do have a redshifting of the momentum of the particles, and this does affect your distribution. So we worked in a non-instantaneous case here. Once we have our phase-space distribution, we can feed this to the cosmology code class. Class will then take the existing equations for non-cold dark matter. It will use the new phase-space distribution, and it can output the resulting matter-power spectrum. So what I'm showing you here is the transfer function, so the ratio of the non-cold dark matter scenario with respect to the matter-power spectrum for a standard cold dark matter scenario. In all the cases, we can see, as expected from non-cold dark matter, that we have a suppression of the matter-power spectrum. So here I fix the dark matter mass to 1 GeV, and what I'm varying is the mass of the primordial black holes at the time of formation. We can see that regardless of the mass, we always have this clean suppression. One very interesting thing to notice here about this suppression is that it always has the same slope. So regardless of which mass we take for the primordial black holes, the shape of the suppression on the matter power spectrum is very, very similar. For reference, I'm also showing here in dashed lines 2 curves corresponding to warm dark matter models. Now, the warm dark matter is a very well-known case, well-studied case that we know induces this suppression on the matter power spectrum. And it's very interesting to note that the suppression induced by warm dark matter models looks very, very similar to the suppression for our non-cold dark matter scenario we're considering here. So focusing for a minute on warm dark matter, we parameterize the suppression in the matter power spectrum with this transfer function, which is what I was plotting on the previous slide. And for warm dark matter models, it's been found extensively in the literature that you can actually describe this suppression with 2 parameters. You can put this alpha nu fit here. Nu is going to give you the overall slope of the suppression, and for warm dark matter, it is well described for nu equals 1.12. And alpha is going to give you the breaking scale, so the point at which the suppression begins in the matter power spectrum. We have this very well established fit for warm dark matter, and this provides a one-to-one correspondence between the breaking scale and the mass of the warm dark matter. So you can do observations of structure on small scales, for an example with Lyman alpha data, and you look for a possible break in the matter power spectrum. If you don't find it, or if you do find it, you can put limits on where the breaking scale would be, and you can directly convert these limits into a limit on the mass. Doing this, we currently have a bound on the warm dark matter mass of somewhere between 3 and 5 keV, depending which result you take in the literature. Now, we wanted to do something similar for primordial black holes, so we started with the same fitting function, this alpha nu. And we already saw in the previous plot that the slope is very, very similar. And we found that we can actually use the same slope. So we can once again take nu equals 1.12. The only thing that's going to change here is alpha. So we have been able to find a fitting formula to define the breaking scale of alpha in the case of primordial black holes. So our alpha now is going to depend on 2 main parameters. We have the mass of the dark matter and the mass of the primordial black holes at the time of formation. And you'll notice that I give 2 different scenarios here for beta smaller than beta critical and beta larger than beta critical. Now, in the case of beta smaller than beta critical, this means that the primordial black holes did not dominate the energy budget of the early universe, and at the time of their evaporation, the universe was still radiation dominated. In the case of beta larger than beta critical, on the other hand, the primordial black holes would have dominated the energy budget of the universe before the time of evaporation and would have triggered an early matter-dominated epoch. But we can see here that because we've now found a fitting formula for alpha PBH, we can reuse existing bounds from warm dark matter, because we can direct the breaking scale that we measure within the matter power spectrum should be the same. So we can use constraints on alpha warm dark matter, so on the breaking scale for warm dark matter, and remap this into bounds on alpha PBH. Now, one cool thing about this, and one reason we want to reuse all existing bounds for warm dark matter, is that getting bounds from Lyman alpha data usually requires running complicated n-body simulations. These can take a lot of time, and they are kind of complicated to run. Whereas by remapping bounds from warm dark matter, we get around this. It means we don't have to do new simulations. We can just use existing bounds and constrain our non-cold dark matter scenario. So this is exactly what we did in the paper. So what I'm showing you here is one of our main results. There's a lot of information in this figure, so I'm going to break it down bit by bit. So what I'm showing here is the dark matter mass as a function of the mass of the primordial black holes at the time of formation. For a given beta, here I've chosen beta 10 to the minus 8. In the paper, we have similar plots for different beta values, and our overall conclusions do not change. So first of all, let me point out this vertical magenta line that is denoted beta critical. As mentioned before, this marks the change between a radiation-dominated universe at the time of evaporation and an early matter-dominated epoch triggered by these primordial black holes. Now, on the left-hand side, you'll see this yellow hatched region, which we denote inflation. This is the lower bound we get on the primordial black hole mass, with the assumption that these were triggered during inflation and converting the tensor to scalar ratio into a bound on the lower mass. On the right-hand side, you'll see we have an upper bound on the mass of the primordial black holes, the blue hatched region, which we denote BBN, This constraint comes from the imposition that all of our primordial black holes have evaporated before the time of BBN. Now, everything along the red line is where we would produce the correct relic abundance that we observe of the dark matter today. Anything above the red line in the red shaded region is therefore excluded, because here we would produce too much dark matter and we would overclose the universe. Then we have the green region. The green region is our new bound from Lyman alpha, where we have taken the conservative bound of 3 keV for the warm dark matter mass. We've used our remapping process. We've converted this into a bound on our primordial black hole / non-cold dark matter. And initially you might be confused by the green region because it lies already in the red region. So what's the point of our new bound? But we also exclude with this green bound any point that lies along the red line and in the green region. So this means we exclude a large region of parameter space where this production mechanism could produce all of the dark matter that we see today. One key takeaway here is that if the primordial black holes dominated the energy budget of the universe in the and triggered an early matter-dominated epoch, they could not have simultaneously produced all of the dark matter that we observe today. So everything in the white zone is still allowed, and we do not extend our green region or our Lyman alpha bounds below the relic abundance because this bound was obtained imposing the correct relic abundance that we see today. In the gray shaded region here on the right-hand side, there could be some unaccounted effects whereby this early matter-dominated epoch would have been so strong that it could have already triggered some small structures. This could lead to nonlinearities today, which we did not account for in our analysis. So in the gray shaded region, there could be something that we didn't take into consideration. So this brings me to my summary. We've already seen this week that we have not yet found WIMPs. This calls for new dark matter scenarios and new production mechanisms. One such mechanism would be primordial black holes producing all of the dark matter via Hawking radiation. Now, the cool thing about this scenario is that even if it only interacts gravitationally, we can still constrain this model with cosmological bounds. Now, because of the effects of the effects on the matter power spectrum are very similar to warm dark matter, so we can completely reuse warm dark matter bounds. With this, we have excluded a large region of parameter space for this non-cold dark matter produced by primordial black holes. And we've ruled out the possibility of all of the dark matter being produced by primordial black holes that dominated the energy budget of the universe. And I hope at the very least this has motivated you to consider these really low mass primordial black holes. So that brings me to the end, and thank you for your attention.
Thank you, Deanna, for respecting your time and for a great talk. So we have a few questions. So I don't know if you can read them from the chat. Otherwise, I'm gonna read them to you.
Yeah, maybe better if you read them out. I don't have the chat open.
From Subinoy, asking if you can explain again how come GeV mass dark matter can give you warm dark matter-like suppression. And
so this one here, you mean?
Absolutely.
Yeah, so it actually turns out that even though the phase-space distribution, in fact, let me go to one of my backup slides here. So the phase-space distribution that we computed, you can see it is very different to the Fermi-Dirac one, which is the standard one you would assume for warm dark matter. But despite the overall tail that it has, this is actually a very low mass region, or a region that doesn't really impact the transfer function substantially. So even though we deviate from Fermi-Dirac substantially, at the momentum ranges that become important when you do the integral, we are still similar enough to Fermi-Dirac that it does have the same net effect. I hope that somewhat answers the question.
I think so.
So you calculated the distribution function for the decay from black hole?
Yeah, so we compute the phase-space distribution of the non-cold dark matter that we obtain here. The full calculation is done in our paper, so I didn't want to go into a lot of details here, but you can follow the full calculation in the paper. And we do really use, we go from the number density of the dark matter to the phase-space distribution, and that's what we then feed to class.
Thanks. Okay, good.
And the second question, Koushik Dutta. Does evaporation process and outcome depend on the spin of your primordial black hole?
So it actually probably does. So I should mention that we considered non-spinning black holes here. There was a paper by Dan Hooper that came out, the other Hooper, that came out in a similar time frame to ours, where they did also consider spin. It doesn't change the results substantially, but it does impact it. So here we considered spin-independent primordial black holes.
Okay. So there are other questions that you can see from the chat. I'm going to take one last, but then I think we should move on, and I'm sure you can answer to them privately.
Yep,
So the last question I'm going to take is, will there be enough gravitons emitted from PBH to give a gravitational wave background?
That is a really, really nice question. The answer would be yes. But it's also, again, I refer to this paper by Dan Hooper that came out at the same time as ours, where they actually considered this scenario. They also looked for gravitational wave constraints. It's not something that we included in our paper, but it is something that you can absolutely do. But at that point, you also then have to consider things like the accretion onto the primordial black holes, which we again did not consider here. So it is another way you can constrain these scenarios. I think the constraints are currently not competitive with the Lyman alpha bounds, but it's expected that in the future, with more gravitational wave measurements, we would be able to constrain this even more.
Okay, thank you very much, Deanna. And now we can move on.